Hey everyone! Today we're diving into one of the most fascinating and mind-bending topics in physics, quantum mechanics. Now, you might be thinking, why is quantum mechanics so hard to understand? Why does everyone say it's so weird? Well, it would be easy to just blame the hard mathematics. And yes, there's definitely some complex math involved, but that's not the whole story. The real reason quantum mechanics feels so alien to us is much deeper than just difficult equations. See, lots of non-physicists actually do understand many complex mathematical concepts when they need to. The real issue is that quantum mechanics describes a reality that's fundamentally different from everything we experience in our daily lives. Let me start by explaining what makes quantum mechanics so different from classical physics, the physics we're used to. In our everyday classical world, things are pretty straightforward. If I have a ball, I can tell you exactly where it is and how fast it's moving. If I measure it, its position, I get a definite answer. The act of measuring doesn't really change the ball itself. In classical mechanics, the state of a system, like the position and momentum of that ball, and what we measure are essentially the same thing. The labels that describe the state are the same labels you get for measurements. But in quantum world, everything changes. States and measurements become two completely different things. The relationship between them is subtle, mysterious, and completely non-intuitive. This is absolutely crucial to understand, and we'll keep coming back to this idea throughout our discussion. Quantum mechanics differs from classical mechanics in exactly two fundamental ways. First, different abstractions. The mathematical objects we use to describe quantum systems are fundamentally different from classical ones. In classical physics, we might describe a particle with simple numbers, its x position, y position, velocity, etc. But quantum states are represented by completely different mathematical objects that have their own logical structure. For example, the concept of a state in quantum mechanics is conceptually very different from its counterpart. Quantum states are represented by different mathematical objects and follow different rules. Second, the measurement problem. This is the big one. In classical physics, if you want to know the state of a system, you just measure it, right? The relationship between the state of a system and what you get when you measure it is very straightforward. In fact, it's almost trivial. The labels that describe the state are the same labels you get from measurements. But in quantum mechanics, this relationship becomes incredibly complex and non-intuitive. When you measure a quantum system, you don't simply read off its state. Something much more mysterious happens. Let me introduce you to one of the most important concepts in quantum mechanics, spin. And I'm going to use the example from about electron spin. Now, spin comes from particle physics. Every particle has properties beyond just its location in space. For example, particles might have electric charge or mass. An electron is different from a quark or a neutrino partly because of these properties. But even if we know we're dealing with an electron, that electron isn't completely specified just by telling you where it is. There's an additional property called its spin. Now, you might naively picture spin as a little arrow pointing in some direction, like a tiny spinning top. But here's the crucial point. That naive picture is way too classical to accurately represent what's really happening. The spin of an electron is about as quantum mechanical as a system can possibly be. Any attempt to visualize it using our classical intuition will completely miss the point. So what do? We abstract away from the classical picture entirely. We can and will study the idea of spin mathematically, but we need to forget that it's attached to an electron. We treat quantum spin as a system that can be studied in its own right. This brings us to one of the most important concepts in modern quantum mechanics, the qubit.
An isolated quantum spin is an example of what we call a qubit, a quantum bit. These are quantum systems that play the same role in the quantum world as logical bits play in defining the state of your computer. Just like your computer's memory is built up from combining millions of classical bits, each storing either 0 or 1, quantum systems, maybe even all quantum systems, can be built up by combining qubits. This is both the simplest and the most profound example of quantum systems. When we learn about qubits, we're learning about the fundamental building blocks of quantum reality. The amazing thing is that by understanding how a single qubit works, we're actually learning about a great deal more. The principles that govern qubits are the same principles that govern all quantum systems. Now let's address the elephant in the room. Why does quantum mechanics feel so impossibly weird to us? The answer lies in scale. Quantum mechanics deals with the behavior of objects so incredibly small that we humans are completely unable to visualize them directly. Individual atoms are near the upper end of the scale where quantum effects dominate. Electrons, which we use as objects of study in quantum mechanics, are even smaller. Here's the key point. Our sensory organs are simply not built to perceive the motion of individual electrons or atoms. We never developed intuition for how quantum objects behave because we never directly interact with them in our daily lives. The best we can do is try to understand electrons and their motion as mathematical abstractions. We can't rely on our usual intuition because our intuition was developed for the classical world of everyday objects. This is why mathematics becomes so crucial in quantum mechanics. It's not just that the math is hard, it's that math is literally our only way to accurately describe and understand quantum reality. In classical physics, we can often build intuition first and then use math to describe it. We can visualize a thrown ball and then use equations to predict its path. But in quantum mechanics, the mathematical description is our intuition. The equations don't just describe quantum reality, they are our primary way of accessing and understanding it. So when you're learning quantum mechanics, don't fight the mathematical abstraction. Embrace it. The abstract mathematical description is actually more real and more accurate than any classical picture you might try to imagine. Let's wrap up what we've learned today. Quantum, not classical. The quantum world operates by fundamentally different rules. States, not measurements. The relationship between what exists and what we observe is mysterious. Qubits are key. These quantum bits are the building blocks of quantum reality. Math is essential. Mathematical abstraction is our window into quantum reality. It's not intuitive, and that's okay. Our intuition evolved for the classical world. The most important thing to remember is that even though quantum mechanics seems weird and counterintuitive, it describes the real world. Every piece of technology around you, from your smartphone to LED lights to MRI machines, works because engineers have learned to harness quantum mechanical principles. Quantum mechanics isn't just an abstract theory. It's the foundation that makes our modern technological world possible. Thanks for joining me on this journey into the quantum realm. If you found this helpful, please like and subscribe, and let me know in the comments what aspect of quantum mechanics you'd like me to explore next time.